machines in history that feel less like aircraft and more like frozen arguments. The Sukhoi T-4 was one of them. On a bleak runway at Zhukovsky in the early 1970s, a titanium Predator sat under a pale Moscow sky, its long needle nose pointed toward a horizon it would never cross in anger. Engineers stood nearby in heavy coats, breath hanging in the air, aware that what they had built was extraordinary. They were also aware, though few would admit it openly, that it might already be obsolete. The T-4 was conceived as the ultimate answer to a specific fear, the fear that the United States had achieved an untouchable strategic advantage in the skies. It was designed to fly at Mach 3, higher than 20,000 meters, fast enough to outrun interceptors and strong enough to endure the brutal thermal punishment of sustained supersonic cruise. It was meant to restore balance through speed. Instead, it became one of the most expensive dead ends of the Cold War. The origins of the T-4 lie in a moment of intense strategic anxiety. In the early 1960s, American aerospace ambitions appeared limitless. The XB-70 Valkyrie promised sustained Mach 3 flight at extreme altitude, theoretically immune to existing Soviet air defenses. Intelligence reports filtering into the Kremlin painted alarming scenarios. Fleets of supersonic bombers capable of delivering nuclear payloads deep into Soviet territory before meaningful interception could occur. Whether those projections were exaggerated hardly mattered. In the Cold War, perception shaped procurement as much as reality. If the United States could field a Mach 3 strategic bomber, the Soviet Union would need something comparable or superior. The response was not merely technical, it was political, psychological, and ideological. Technological parity symbolized strategic legitimacy. The Soviet leadership initiated a competitive program inviting proposals from its most powerful design bureaus. Tupolev, the established giant of Soviet bomber design, offered a more conservative approach, built around variable geometry wings, balancing takeoff performance with supersonic dash capability. Sukhoi, traditionally associated with fighters, presented something far more radical, a fixed delta-wing aircraft constructed largely from titanium, optimized from inception for sustained Mach 3 cruise. Where Tupolev emphasized practicality, Sukhoi embraced extremity. In a rational procurement environment, the safer design might have prevailed immediately, but the Soviet system was rarely governed by pure rationality. Both bureaus received funding. Prototypes would decide the victor. It was a Darwinian contest disguised as engineering competition. From the beginning, the T-4 was a metallurgical gamble. Sustained flight at Mach 3 generates skin temperatures exceeding 300 degrees Celsius due to aerodynamic heating. Conventional aluminum alloys lose strength at those temperatures. Steel adds prohibitive weight. The solution Sukhoi pursued was titanium, specifically high-temperature alloys capable of retaining structural integrity under extreme thermal loads. Approximately 75% of the T-4 structure was titanium, an unprecedented proportion for an aircraft of its scale. This decision demanded an industrial transformation. Titanium is difficult to machine, prone to work hardening, and reactive with oxygen at elevated temperatures. Welding required controlled atmospheres. Tooling wore rapidly. Production tolerances became unforgiving. The T-4 did not simply push aerodynamics forward, it forced the Soviet industrial base to evolve in parallel. Aerodynamically, the aircraft embodied the pure logic of supersonic efficiency. Its delta wing, swept sharply at roughly 60 degrees, was selected to exploit compression lift at high Mach numbers. The long fuselage minimized wave drag, and the engines were integrated into the wing roots to reduce interference and frontal radar exposure. Every contour served speed. Unlike subsonic bombers optimized for endurance or payload flexibility, the T-4 was built as a strategic sprinter. It was meant to climb high, accelerate to Mach 3, and deliver its payload before defensive systems could respond effectively. In theory, altitude and velocity were its shield. In practice, achieving stable, sustained supersonic cruise required solving complex intake and propulsion challenges that few had confronted at this scale. Power came from 4 RD-36 turbojet engines, each engineered specifically for prolonged high-speed operation. Supersonic intake management became one of the program's defining technical hurdles. At Mach 3, incoming air must be carefully slowed and compressed before entering the compressor stages of the engine. Variable ramps and shock cones, positioned within massive rectangular intakes, performed this delicate transformation. The geometry had to maintain precise shockwave placement. Even minor instability could trigger compressor surge and thrust loss. Early tests revealed just how sensitive this balance was. Wind tunnel campaigns stretched for months as engineers refined intake contours and control algorithms. At extreme speeds, the intakes effectively performed significant portions of the compression work, demonstrating how propulsion at Mach 3 is as much an aerodynamic challenge as it is a mechanical one. Fuel management presented its own complexities. The T-4 carried roughly 65,000 kilograms of specialized high-temperature kerosene distributed throughout integral wing and fuselage tanks. This fuel served dual roles: propulsion and thermal regulation. Avionics and environmental systems transferred heat into the fuel before combustion, using it as a mobile heat sink. However, heating the fuel increased vaporization risk, especially at altitude. Engineers developed automated transfer systems to maintain the aircraft's center of gravity as fuel was consumed. Delta wing aerodynamics cause shifts in aerodynamic center across varying Mach numbers, requiring careful mass distribution to preserve stability. The solution was a computerized sequencing system that continuously balanced tanks in flight, a sophisticated capability for its era. One of the most distinctive features of the T-4 was its droop nose. At supersonic cruise, a long, pointed nose reduced drag and improved aerodynamic efficiency. During takeoff and landing, however, that same configuration severely limited pilot visibility. The answer was a hydraulically actuated nose section capable of tilting downward at low speeds. Designing this mechanism was deceptively complex. The hinge had to withstand aerodynamic heating, seal perfectly at high speed, and maintain structural rigidity under pressure loads. Optical clarity of the cockpit glazing had to be preserved despite temperature fluctuations. The droop nose would later influence other Soviet designs, but on the T-4 it symbolized the broader engineering theme. Solving one problem often created another layer of intricacy. Inside the cockpit, the crew sat in tandem within a pressurized escape capsule rather than conventional ejection seats. At Mach 3, dynamic pressure outside the aircraft renders standard ejection fatal. The T-4's capsule system was designed to detach from the fuselage, deploy stabilization chutes, and descend intact. The crew would remain protected within the sealed module throughout descent and landing. It was an elegant concept, reflecting awareness of extreme operational conditions. Yet it remained largely theoretical, never validated by real emergency deployment during the program's brief life. The T-4's maiden flight occurred on August 22, 1972. Test pilot Vladimir Ilyushin conducted a cautious 35-minute sortie, keeping the landing gear extended and limiting speed. It was not a demonstration of Mach 3 capability, but of structural viability. Subsequent flights gradually expanded the envelope. Over roughly 2 years, 10 flights were completed. The aircraft achieved Mach 1.36 and altitudes approaching 17,000 meters, impressive milestones for a first-generation prototype built from advanced materials. Engineers believed higher speeds were achievable with continued testing. Technically, the trajectory appeared promising. Strategically, however, the environment was shifting. The XB-70 program, which had partly inspired the T-4, was canceled in 1969 after only 2 prototypes were built. Surface-to-air missile systems improved dramatically during the late 1960s. Radar networks expanded. Intercontinental ballistic missiles and submarine-launched ballistic missiles offered faster, more survivable deterrent capabilities. Strategic doctrine evolved away from high-altitude supersonic penetration toward missile-based deterrence and eventually low-altitude or stealth-oriented bomber concepts. The very logic that justified Mach 3 strategic